discussion.
First time in Boulder.
Slowly you can start. People are still arriving, but it's nice.
Okay, I'll try to start slowly. Okay, so yesterday I introduced this embedding formalism, so I hope I convinced you that conformal field theories want to live in this null cone. And if you do that, then you're basically studying conformal field theories in any conformally flat manifold at the same time. Okay, so we saw that primary operators just become operators that satisfy this scaling property along the light rays in this embedding space, and then we saw that when you want to go to some particular physical space-time, you just choose a section of this light cone, and we discussed in particular these two sections that you also studied in conformal field theory, just one that takes you to RD and another one that takes you to the cylinder. Okay, so I should proceed to AdS. So now I want to convince you that anti-de Sitter space-time fits very naturally in the same embedding space. Okay. So again, I will be doing the Euclidean version, and so Euclidean AdS, if you want, is just the hyperboloid. So you take these points xa in this embedding space, d plus 1, 1, and you just impose that x square is minus r square, okay, where r is going to be the radius of AdS, and x naught is bigger than 0. Okay, so let me just draw you a picture. So let me draw x naught here, and now the other spatial directions. So this condition just tells you that AdS is this. So let me try to draw this. So it's this hyperbola that, in particular, it approaches the light cone when the points go to infinity. Okay. So just from this picture, we already conclude that the boundary of AdS is basically the space of light rays through the origin of this embedding space. Okay? And of course, this by construction, this space preserves all the Lorentz symmetry of this embedding space, right? So the same SO d plus 1, 1, the same group that was the conformal group is exactly the isometry group of AdS, right? Just because this hyperbola is preserved by Lorentz transformations. And okay, now I'll just want to show you more other familiar faces of this space. So I'll have to quickly introduce Poincaré coordinates. So they are very similarly related to the Poincaré section of the light cone. So let me just so these coordinates are labeled by d plus 1, I mean, there are d plus 1 coordinates, right? Because the d plus 1 dimensional manifold. Okay, so maybe I should make this clear. This is d plus 1 dimensional AdS. And so I'll just write it like that. Okay. So again, I'm using this split of the coordinates 0, mu, d plus 1, where mu runs from 1 to d. Okay. So I'm doing the same over there. So you can easily check that if you take the square of this, you get r minus r squared. So it's a parameterization of this hyperboloid. And more interestingly, you compute the induced metric. So you just, well, as before, right? You just take eta AB, dxa, dxb in these particular coordinates. And what you get is the standard well, I'll just contract, right? But it's the standard form of the Poincare metric. So in particular, from this picture, you see immediately that so AdS is conformally equivalent to R plus cross RD, right? So that's this picture that Pedro was drawing, that most of you probably saw already. So, well, maybe like that. So let's say this is RD, and now you have Z going from 0 to infinity, and that creates your AdS space, and essentially the metric blows up as you approach this boundary, this conformal boundary. Okay, and what else do I want to say about this? Yeah, of course, if you look at this vector, you see that as so as z goes to 0, this vector approaches the precisely the form of the Poincare section, right? So you are parameterizing this hyperbola with some coordinates, and now as z goes to 0, you are going to infinity. All vectors are becoming very big, but you go to infinity in a particular rate such that you are approaching, I mean, there's some diverging factor times precisely the Poincare section of the cone, okay? So this is the generic, so well, it will be clear now. So I also have to do the same for global coordinates. So here you'll have, again, d plus 1 coordinates. So you will have a Euclidean time that runs over all values of r. Then you will have a radial coordinate that is just positive. And then you will have a point in the unit sphere. And so, again, the coordinates, the parameterization here is just r and in this case the metric looks different. So the metric in this case is just and so as before, now if you take this point and now you go to infinity using these radial coordinates, so if you send rho to infinity, basically you have some factor that is blowing up times a null vector, which again is precisely the null vector that corresponds to the global section of the light cone. Okay, so this is, okay, I should also draw the other picture. So from this point of view, AdS should be thought as the interior of a cylinder. So Euclidean time runs upward, like you see here, but then there is this rho equals 0 is this center, so rho is a radial coordinate that runs from 0 to infinity at the boundary, and each constant time slice is basically this d-dimensional hyperbola, which at infinity contains this sphere as d minus 1. Okay? So it's basically the interior of the cylinder that you studied in conformal field theory. Yes?
Is there an analogous story, like is the Poincare patch just some
No. So in Euclidean space, these Poincare coordinates cover everything. Or maybe you miss one point, but well, no, they cover everything. You can easily check that basic. Yeah. I will not do it here. If you think about it carefully, you'll see that you cover everything. But I'll comment on this. In Lorentzian space, it's different. Okay, so I mean, I had to do this. It's a bit boring, this kinematics, but the point is that here, AdS has a boundary, but it doesn't have. But the boundary is just a conformal boundary. Okay, so it doesn't have a metric by itself. It only has a conformal structure. So it has a metric up to a Weyl transformation. So going to the boundary of AdS in different ways. So for example, there we chose to go with z going to 0 and x. For each x we send z to 0. Then the boundary looks like half of flat space. Okay. If you go to infinity at a different rate, then the boundary looks like a cylinder. Okay, so you can make the boundary of AdS be any conformally flat manifold, exactly like you can make the section of the null cone to be any conformal flat manifold. Okay, this is just the same statement. Okay, any question about this simple kinematics? Very good. Good. So let's then discuss. Okay, so now in the next minutes I'll make a parenthesis and I'll work in Lorentzian AdS, and then I'll go back to Euclidean. But for a while I need to discuss Lorentzian AdS because I want to discuss some intuition of what happens in real dynamics in this space. Okay. So what is Lorentzian AdS? So now we change the signature. So this embedding space is going to have 2 times. So it's our d comma 2. And but we still impose the same constraint. So x squared, if you want, which now, okay, let me be. So I changed the sign in the last coordinates. Okay. So now it's this hyperboloid, and so maybe I can draw it here schematically. So suppose I draw. Let me try to draw first. Something like that. Okay, so let's say this is x0 and this is xd plus 1. So you have both these coordinates are time-like, and you, of course, you can rotate between them because only the square appears in this constraint, and here you have all the other spatial coordinates. So in fact, this definition would say that there is a closed time-like circle. Okay? So this circle here is time-like because I'm just moving in a plane which both coordinates are time-like, and it's closed. Okay. So what we do is we take what's called the universal cover of this space, and basically instead of time running, so time natural. Well, before saying that, let me introduce this time. So you can just go directly from the Euclidean to the Lorentzian just by analytic continuation, right? So you just put an I in this coordinate, so that changes the sign, and then you also do I want to plus or minus like that? Okay, so you just introduce a time t, which is just it, and so here this just becomes cosine t, and this just becomes sine t. Okay, so that's your parameterization, and here, of course, it just becomes minus dt squared, right, instead of d tau squared. So that's your Euclidean, your Lorentzian metric in global coordinates. So then this time t, as you can see here, it's cosine and sine, just rotates these two time-like coordinates. So this time would naturally live from 0 to 2 pi. So you take this universal cover, and so time actually is going to live from in R, right? So you just unroll this circle. Okay, so so the next thing I want to do, so I'll just rewrite the metric for the last time, I promise, in the following way. So the only thing I did was I changed this radial coordinate rho to another radial coordinate r, such that now r is compact. Okay, so r lives from 0 to pi over 2. Okay, and when r approaches pi over 2, rho approaches infinity. So you cover all of AdS using these compact coordinates. Okay, so this is the conformal compactification of AdS, because now I have a metric where the coordinates, this radial coordinate has a finite range, and this metric is conformally related to the metric of AdS. Okay, so now that I've done this, I can draw a picture and tell you basically all the important physics that happens in AdS. So the picture is just this cylinder. So again, time runs upward. Now it's, sorry, I should correct me. So now it's Lorentzian time. And so first thing that you should notice is that what happens to light rays in this space. Okay. So that's very obvious once you write the metric in this form, right? So here r equals 0 is the center of this cylinder. And so you go from r equals 0 to r equals pi over 2 at the boundary. So basically, since you already have this form, if you set it to 0, so a light ray that moves just along the radial direction will just move at 45 degrees here. So you go from minus pi over 2 to pi over 2, so it will move from one boundary to the other in a global time interval equals to pi. Okay? So that's the first important feature, is that if you sit here at the origin and you send a light ray away from you, it will go to the boundary and reflect back to you after a time pi, okay? After a finite time. Good. So, and in fact, you can also, well, there's some, you should play with this for a while. I don't have time to do all the details, but for example, it's very easy to see that all light rays here in AdS are actually also light rays in the embedding space. Okay, so they are literally just light rays in the embedding space that are contained inside AdS. And you can easily show that all of them that are emitted from a point, basically just all of them merge on the other side after a time pi. Okay? So this is actually very important, because from the point of view of this boundary, right, you don't want light rays that travel to through the bulk to, right, so this, sorry, the boundary here is this sphere, right, SD minus 1. Okay? So suppose I have this CFT living on the boundary, and now you create some excitation, say at the North Pole. Okay? So this is a relativistic theory, so it will take some time for this excitation to reach the South Pole. Okay? And what is the time? How long will it take? Pi, right? If I take the sphere with radius 1, it will take pi. Okay? So the same happens through the bulk. Okay? So that's very important, because otherwise you'll have a problem with causality, that you could have signals traveling fast if they go through the bulk. Okay? Good. So the second thing, so this is light rays. What about massive particles? Well, obviously, there is a time-like geodesic which is just sitting at the center. Right? Actually, you can just draw it here. It's just the intersection with this. Right? It's just that circle, but unwrapped. Okay. So now it's very easy. So once you know this, since this space has all this SOD, all this Lorentz symmetry, you can just, if you know one time-like geodesic, you can just boost it and generate all the others. Okay. So if you start playing that, so for example, here you can do a boost that changes this circle to some other circle, for example, that goes like that and then comes back like that, something like that. Okay. So that here will just correspond to some particle that now it's moving here with some velocity, and then it will start making a periodic motion around the center of AdS. So the other important property that actually follows from that picture is that the period is delta t equals 2 pi. Okay? So a particle oscillates around the center of AdS, always with period 2 pi. And you can also do things rotating by taking further boosts into orthogonal directions, but it's always the same. All time-like geodesics are periodic with period 2 pi. Okay, so the conclusion is that AdS really acts like a box. Okay. So this was the statement I told you yesterday. So here you can see it very explicitly for the motion of classic particles in this background. Any question about this? So I should emphasize that this is a very, very remarkable box. Because you see, it's a box that, I mean, it's literally a box. You are there, you send light, the light reflects and comes back to you. But it does not have a center. Any point is equivalent to any other. Okay? So I find it really hard to imagine a box with walls and no center. So. Okay, so final comment, which is related to the question I was asked before. So what happens in Poincaré coordinates now in this Lorentzian setting. Okay, so again, you can write something basically what I wrote before. You just have to reshuffle a bit the position because of what became time-like. So here now I'm saying alpha runs from 0 to 1 to d minus 1. Sorry, minus 1. So the boundary is really d-dimensional Minkowski space. So in particular, x squared is now eta alpha beta x alpha x beta. Okay, so you can check that solves the constraint. And so the only comment I want to make here is what I was asked before. So maybe I can draw it here. So the point is that now these coordinates do not cover the entire cylinder. Okay, so they cover a region with this shape. So if you send z to 0, you still go to the boundary. So z equal to 0 is the boundary. But if you send z to infinity, you basically approach these light-like surfaces, z equals infinity, and here also z equals infinity. You can actually check that when z goes to infinity, this surface is just a null surface. So when you sum these two coordinates, right? xd plus xd plus 1 equals 0. When z goes to infinity, you approach this null surface. And basically, so this is the region covered, and that's what's called the Poincaré patch. Okay, so you will see that discussion often in the literature, so I need to call your attention to that, but it's not going to be very crucial for us. The point, this is the origin of the name, right? Because in Lorentzian coordinates, in Lorentzian signature, Poincaré coordinates only cover a part of space, so that's why the other ones are called global. Okay? In Euclidean signature, that distinction doesn't make much sense. Good. Any question about this? Yes. Yes. It's a boundary condition that you impose, yeah, with a natural boundary condition. Okay, so let's continue a bit longer in this Lorentzian signature, and now I want to discuss what happens to quantum mechanically. Okay, instead of just studying quantum classical geodesics, I want to study wave functions of particles in this space to see what features does that bring. So I want to look at the spectrum. I want to compute the spectrum of a scalar field. So basically, I want to solve this equation, the Klein-Gordon equation, with some mass. So in the notes, there is some exercise. You can actually do it more or less directly using these global coordinates. You get some wave functions, and you see how this works. But here, I want to do it in a more indirect route. So we will solve this equation, but before, let's just go through two facts. So first fact is that you can compute, I want to compute the quadratic Casimir. Okay, so these GABs are just the Lorentz generators, okay, which basically, if I want to act on some scalar field, they are just the standard representation. Okay. And now I want to take the square of them, so consider the quadratic Casimir. And so it's a simple exercise just to contract these indices, commute some of the derivatives, and show that this is equal to the following. Okay, so what's the meaning of this equation? So, well, even here I could also make the comment. So phi is a field that lives in AdS. Okay, but I'm writing this J, this Lorentz generator, has some differential operator that takes derivatives in the embedding space. Okay, so formally I am extending this field phi to the full embedding space, right? Okay, outside of AdS. But that's really just formally, because actually this combination, JAB, is a vector field that preserves AdS, so this derivative will be independent of the way you continue the field outside of AdS, okay? So you can just compute it in any continuation you want, and it will only depend on the actual value of the field phi on the submanifold, which is AdS, okay? Okay, so this is the first fact. The second fact that I want to use is the following. So now, suppose I consider this embedding space, and I foliate it with several AdS's. Okay, so with many. So I foliate this RD, 2 with AdS, whatever, leaves or something. Okay, surface of AdS with different radius. Okay, maybe I should write that with different. So here, once you do that, this is basically like going to spherical coordinates, right? So you can write the Laplacian. Now the full Laplacian in the embedding space is basically going to be like the radial derivative, the radial part of the Laplacian, plus the Laplacian in AdS, right? This is like spherical coordinates. It's nothing more than that. Okay. But the point is that once you do that, so these derivatives here are precisely a derivative along the norm of AdS. So it's x dot dx. So it's just r d by dr in the other language. So you can just identify, and the conclusion is that this quadratic Casimir acting on a scalar field phi is nothing else than just the Laplacian acting on a scalar field. Okay, so they are just the same thing. So if you want to solve this Klein-Gordon equation, it's basically telling you that the mass in units of the AdS radius is the Casimir eigenvalue, which you learn that for a scalar operator is just delta minus d. Okay, so that's the first thing you learn, and it already tells you that all solutions of this equation will be in the same representation of the conformal group, of this Lorentz group, right? They have the same value of the Casimir. Okay. Okay, so but now we want to solve it more specifically. We want the spectrum of this scalar field in this, I guess, in these coordinates here, okay, or in those ones. So with respect to global time. So what is that? So that's very easy. So this global time translation is just the rotation in the x0 xd plus 1 plane. Okay, so it's very easy to see that this. If you want E d by dt, which is what's going to be my Hamiltonian, which actually is the dilatation operator. In the standard language, that dilatation operator is the Hamiltonian in the cylinder. It's just the generator J0, jd plus 1. So in my notation, I think there's a minus here. Okay, so I want to get the spectrum of this operator, but we already know that the algebra, the Lorentz algebra, is just the conformal algebra. So we can identify a generator which is like P mu, which is J mu 0 plus I J mu d plus 1. And we can also identify a generator which is like K mu, which is J mu 0 minus I J mu d plus 1. And of course, the Lorentz generators, let's say M mu nu, the rotations, are just the same. Okay? So what we want? Clearly, so we want something that is some representation of the conformal group with this value of the Casimir. But now we want the spectrum of this dilatation generator. But we already know the algebra, right? We know that if we act with K mu on some state, that will lower the eigenvalue of this dilatation generator, of this Hamiltonian. So it's clear that if you want to compute this spectrum, and if you want it to be bounded from below, you have to impose that K mu is equal to 0 on the ground state. Okay? So that immediately gives you the ground state. You impose that K mu is equal to 0. So where should I write that? I used all the board. Yes?
How do you get the expression for P mu and K mu?
So basically, I mean, you know that the Lorentz algebra is this SOD plus 1, 1, right? So you just have to identify the linear combination of the generators that give you the right commutation relations of the algebra, right? I think David even had an exercise that he was doing that, right? Maybe the other way around, putting these guys together to form the Lorentz algebra. So this is just inverting. So I guess I need to erase. So I'll try the systematic approach to erasing. So is there any question while we have this little break?
Is the spectrum of the quadratic Casimir exactly the same as the spectrum of the
It's liver in a bigger space. No, but again, these Lorentz generators preserve AdS, right? They are derivatives. I'm writing them as derivatives in the embedding space, but actually they preserve AdS. So the Killing vector field is tangent to the hyperbola. So what we'll see is that basically the spectrum of a single particle in AdS is exactly the same as a conformal family. Well, I basically am already there, no? Good. Okay, so if when I look at the ground state, so the minimal energy state, so this ground state should be annihilated by this K mu, so let me call it phi 0, but it should also be an eigenstate of the dilatation generator of the Hamiltonian. Okay. So actually, I can call it an exercise, but it's a simple one. So you can just check that the wave function, so this phi 0 that solves these two differential equations, is of the form like that. Okay. So it's clear that it has to be like that because it's an eigenstate with the energy delta of this Hamiltonian, and the shape in transverse space, it follows from this equation. Okay. So there's an exercise in the notes that helps you to do this very explicitly. You can write these differential operators in global coordinates, and then you see what you get. So, but actually, there's a nicer way of writing this that makes things more transparent. Well, at least once you get used to this embedding way of thinking, which is like that. So why do I like that? So first of all, it's clear that this is still an eigenvalue of the dilatation generator with weight delta, because the dilatation generator was just rotating x0 and xd plus 1. So this is just the complex combination that is an eigenfunction of this rotation, right? Just rotates by a phase, and that's the dimension you get. It's also clear that solves this differential equation. Sorry, that solves the... Did I erase that? That would be a big mistake. Did I do that mistake? No, good. It's also clear that it solves this equation, okay? Because this equation is just that the Casimir, which is given by this differential operator, is equal to delta d minus delta. But look here. So suppose the function is harmonic in the embedding space. So this first term is 0, okay? So it's clear that this is true for this function, right? Because this is a combination of two coordinates which solves is like, I don't know, it's like x minus t is a solution of the wave equation. So here it's x minus iy, it's a solution of Laplace equation, okay? Any function of x minus iy. So this is clearly 0. And now this just measures the weight in the embedding space, x d by dx. But the weight is just minus delta, right? Because it's an homogeneous function in the embedding space. So here you also get minus delta, so you're done. You get the eigenvalue delta d minus delta, or delta minus d. Okay? So this equation is very useful, because if you want to write functions that solve the Laplace equation in AdS, you can immediately try to, it's equivalent to look for functions that solve Laplace equation in the embedding, and they are homogeneous with some given weight that is related to the mass of the part. Okay, so that's a useful trick to know. Okay, so what about excited states? Well, it's exactly like in CFT. So since the equation is just a Casimir, if you act with any of the generators on the ground state, that will not change the value of the Casimir, right? The Casimir commute with all the generators. So you can just create excited states by acting with P, right? Because P increases the energy. So the most general, you can take like a traceless combination of LPs, and then you can take P squared to the n, acting on this phi 0, and it gives you basically the most general excited state of this particle in AdS. Okay, so the spectrum is just the ground state spectrum plus the number of derivatives, so plus L plus 2n. Okay, so these are just integers. So the conclusion is that single particle states of phi in AdS are in one-to-one correspondence with a conformal family Okay, so you have a primary and all of its yes.
What corresponds to the other Casimir?
That's you mean for you mean that's in Poincaré, that's for quantum field theory.
Yeah.
I mean there's a quartic Casimir that you can make from these J's, but yeah, here it's not very relevant. I mean you will get some number, but yeah. Good. So this algebraic way of doing it hides all these details. Very good. So basically, I'm imposing that the field decays at infinity. So when it approaches the boundary, it goes to 0. And actually, the equation tells you that it has to go to 0 with no. That I'll tell you about tomorrow. No, here no. I just want to do states. So states don't go to any non-trivial boundary condition. States just go to the trivial boundary condition. Okay, so just a quick comment. So what about multi-particle states? Okay, what about multi-particle states? Let's say of a free field, right? So if it's not free, it's hard to do multi-particle states, but of a free field in AdS. Well, so do you know the answer? See if you are awake. What did we saw yesterday? We saw that in some CFTs, it's very natural to put together operators, and basically they act as free fields, right? That the dimension of the operators you put together is just the sum of the dimensions. So here is exactly the same, right? You have a single particle. If they are free, you can put 2 particles or 3 particles, and the energy is just the sum. Okay, so this is as the same structure as multitrace operators in large N CFTs. Okay? If it's free, it's really like infinite N. I'm not considering any interactions at all in this picture. 47. Okay. Any questions about this? Good. So now I want to study more directly quantum field theory on this AdS space, and I close the Lorentzian parenthesis, so I go back to Euclidean. Okay, so, and I'll continue with this scalar field. So I'll just write the action, some integral over AdS, and I'll just start with some free scalar field of mass m. For now, I'll start like that. And actually, I'm also going to set r equal to 1, so I'll measure all lengths in units of the AdS radius so that I don't have to carry that number around. So if it's a free field, the only thing you have to know to compute correlation functions is to know the propagator. Okay, so what's the propagator? So the Euclidean propagator is just the Green's function, so I'll call it pi from x to y, and it has to obey this equation, where this is a d plus 1 dimensional delta function with the AdS measure. Okay, so it's basically an exercise for you to show. So I'll write here. Exercise for you is to show that this propagator. So first of all, there's one obvious thing that you can say is that this propagator is between 2 points in AdS, so it has to preserve the isometries of AdS. So it can only be a function of x dot y, right? There's no other invariant that it can depend on. So actually, it's better to write that as x minus y square. So it's the same thing because both x square and y square are minus 1, right? Because that's the condition. That's the condition that you are in AdS. I'm setting r to 1. So this is the only variable that it can depend on. So the exercise is to show that this propagator from x to y is given by some constant and moreover, you should also show that this constant C delta is given by Okay, let me just give you some guidance into this exercise because you shouldn't do it like brute force. So how to compute this? So first thing, yeah, that's why I was avoiding this. Okay. So first thing, what you should do first? First, you should find an actual differential equation. So you should reduce this differential equation in x and y, that is a bit like many variable, you don't know what you're doing, to an actual differential equation just as a function of this elementary variable, this zeta, right? This chordal distance. So to do that, you just have to use these two equations that I am erasing, right? So the easiest way of acting with the Laplacian is to use this equation. So this is nothing else than the Laplacian acting on phi. So if you write in terms of embedding space coordinates, this is the most useful way of writing the Laplacian. Okay. So this, let me call this star. Okay. So you should use this equation to get differential equation in the variable zeta. Okay, that's the first step. Now, once you have just an ODE, just one variable differential equation, you just have to impose this boundary condition that the propagator from x to y should go to 0 when the distance between x and y goes to infinity. Okay, so that's the boundary condition that selects one solution of this second order ODE. And then the last thing is to fix the normalization of the propagator. So of course the propagator has some normalization because it satisfies an equation with a delta function. So you just have to integrate. So fix the normalization using just integrate that equation around the point y. On y around the, what do I want to say? No, on x, of course, around the point y. Right, and now here you can integrate by parts and measure the flux, and you can fix the normalization like that. Okay, so this is a nice explicit exercise that you can do get familiarized with the fact that embedding formalism is actually useful to make calculations. Okay, so once you have the propagator, if the theory is free, then you can compute all correlation functions. Right? This is exactly like in flat space. So 2-point function is just a propagator. Right? And you can even draw diagrams. So you have some point in AdS, x, and some point y, and you draw a propagator from x to y. So this is a common notation. I'll draw AdS as the interior of this ball. Okay. Can actually make it precise. There's some coordinates where the boundary of AdS looks like a d-dimensional sphere. So that's a natural way of writing. And well, of course, if you take say a 4-point function, then it's just given by the sum of all 1 to all weak contractions, right? 3, 4 plus other weak contractions. Okay, so that's very simple. That's just like in flat space. And similarly, if you add small interactions, so let's just add here let's just add a cubic interaction, for example. Then if you add a small interaction, now you have Feynman diagram, more Feynman diagrams. So for example, you can compute a cubic, a 3-point function. And this 3-point function is basically just going to be given by this first diagram. So let me just draw the diagram. So you have those points x1, x2, and x3, and you connect them to a point x in AdS, where you put this cubic vertex, and you just integrate over AdS. Right? So each one of these lines is the propagator, and you have 3 propagators integrated. Okay? And, well, this is exactly like in flat space. The only difference is that you're using a propagator which is different from the Feynman propagator in flat space, and you're integrating over AdS instead of integrating over flat space. So it's exactly the same type of Feynman rule. So, okay, so we need another break. Okay, time for questions again. So, okay, so maybe I should, so this is like embedding space notation. So let me write, well, here you don't have to change anything, right? It's just Laplacian in whatever coordinates you choose, Laplacian in AdS, right? And here is whatever coordinates you choose from one point to the other. Here, it's more natural, right? In a given coordinate system, you usually write the delta function as delta, the standard delta function, d plus 1 of all coordinates. Let's say, let me call w1 and w2, sorry, minus w2. And then you divide by the square root of the metric at w1, right? That's the standard way of writing a delta function in curved spacetime, right? Such that when you integrate it with the measure, you get 1. So if you want to do it in specific coordinates, this is the delta function you should use. But if you do it like that, it's actually not very important, because at the end, the only thing you need to compute is, so here you have, so this field phi is going to diverge when, sorry, this is the propagator, right, from x to y. So this propagator is going to diverge when x approaches y, and you just have to compute the leading term that dominates this integral, right? You can take the size of this small ball around y to 0, and basically the contribution will come by integrating by parts this Laplacian, and it's going to be the flux of the derivative of the propagator. More questions? No more questions, okay? So now the magic will come, because I can take the limit where these points, so I take this correlation function, which is just like in flat space, but now I take the limit where the points go to infinity, so approach the boundary of AdS. Okay, so in this picture, I just take these points going to infinity. So more precisely, so I introduce the following operator. So it will be a function of a point P, which is a null vector, so it's a point in the boundary of AdS. And this operator will be defined by the limit, when lambda goes to infinity, of the field phi computed at the point x equals to lambda p. Okay, so it goes in that direction. Of course, you have to add here some small piece such that the square of this is -1. But the point is that this thing is finite. Okay, it does not scale with lambda. So lambda is going to infinity. So x is going to lambda p plus some epsilon such that x is still in AdS. And you just rescale it by lambda to the delta. To get a finite answer, you have to do the limit like that. Okay? And actually, for convenience, if you want to get this operator to be precisely normalized to have unit 2-point function, you just divide here by the square root of c delta. But okay, that's just a normalization. It's not crucial. Okay? So given this definition, I can compute 2-point function of this operator, O of P1, O of P2. So I just go to the 2-point function of phi and take the limit. Okay? And it's very easy to see. So the 2-point function was just a propagator. So when the distance between x and y goes to infinity, this zeta goes to infinity, the chordal distance goes to infinity. So this argument goes to 0. Hypergeometric function at 0 is 1. So you just get this 1 over delta behavior. And then the c delta cancels with this square root. That's why I put it here. And you just get 1 over -2 p1 dot p2 to the delta. Check. No? That's precisely the 2-point function you want to see in a conformal field theory. So in pictures, you have this 2-point function from P1 to P2 with some propagator that stretches all the way from one boundary point to the other. Actually, you can just see from this definition, it follows directly that O has the homogeneity properties that you want. Okay, so it's automatic from this definition that O satisfies the scaling property of a dimension delta operator in a conformal field theory. Okay. Well, of course, by construction, all the correlators of phi were SOD plus 1 invariant. So in the limit, they're still invariant. So the correlators of these operators that I just defined will be SOD invariant. Okay, so that's also a property that you want, and it's guaranteed by this construction. And you can even get reflection positivity, right? You can get unitarity conformal field theories if you start from a quantum field theory in AdS which obeys reflection positivity. Okay, so you don't lose this property when you send the points to infinity. Okay, so let me just. So for example, if you want to be a bit more detailed, so for example, the 3-point function now has a bit more structure. So what is the 3-point function? So like it's actually here. So we can just take the limit of this one. So this one is the first term in this weak coupling expansion in this small coupling G. So this is going to be G C delta to the 3/2, this normalization. And then this integral so from point P1, P2, P3, and then there's a point X in AdS that is being integrated over. Okay. So these kind of diagrams, they are usually called Witten diagrams. So they are just Feynman diagrams in AdS. So there's both points points in the bulk that are being integrated over their interaction vertices, and then you have external points that are connected to the boundary of AdS. And so the way these things are connected is through this what's called a bulk to boundary propagator. So this bulk to boundary propagator is just the limit of the bulk to bulk propagator, so this propagator that we already studied, when one of the points goes to the boundary. Okay, there's nothing more than that. So if you look at that and you take the limit, you just get C delta over -2. So for example, this one would be P3 dot X to the delta. Okay, so that's your bulk to boundary propagator. And now if you want to compute this 3-point function, you have to compute this integral over AdS of the product of 3 of them. Okay. So in the notes, there is an exercise to actually compute this integral. It's an interesting exercise, but it's actually an exercise that is just to compute a number, because you already know the answer. Because from all those properties, you already know that this 3-point function of scalar primary operators is fixed by conformal symmetry. So actually, you already know that this must be equal to, I think in this case, -2 P1 dot P2, -2 P1 dot P3, -2 P2 dot P3, and all of them raised to the power delta over 2. Right? Because there's some constant that's what the exercise is about, to compute that number, but the rest is automatic just from conformal symmetry. So this is the only combination that is Lorentz invariant and has weight minus delta in every point. Okay. Good. So this is, I'm doing perturbation theory, so this is plus order G cubed terms. Yeah, there would be, if you're doing quantum field theory, there will be more corrections to this. Yeah, this is the first diagram. It's still guaranteed to hold its form because, well, okay, let's be more precise. It's guaranteed to hold the form of a 3-point function of a conformal field theory what can happen is that in this bulk quantum field theory, when you introduce this coupling, you can have mass renormalization for the field, which means that the dimension will also change. Okay, so you can have some change in the dimension as well as some change in this constant. But that's the only things that can happen, because those are the only things compatible with the symmetry. Right. So if you go to higher orders and you renormalize the bulk actions, I mean, this you can compute, right? It's like in flat space, the UV divergences are exactly the same. So you have some correlator. So this correlator will satisfy all those properties. So when you take this limit, you will just go to here. Sure. If you expand in G, you will see. At leading order, you don't have any mass renormalization from this diagram. Okay. So delta doesn't change. It's just that. Yeah. Okay. So what's missing? I have some board here. Very good. So what's missing? One thing that is missing is a convergent OPE. Well, actually, I want to argue that you also have a convergent OPE, but I need to argue that. I still didn't convince you about that. So the argument, given the 4 minutes I have, it's gonna follow from basically one picture. So let me draw this picture more or less carefully. So let's see. So this is AdS, and I want to draw here. So let me think. So the embedding space. Imagine this is like the x d plus 1 direction of the embedding space, and this one here would be like x mu, and like outside the board would be x0. Okay. So for example, a surface tau equal constant is just to cut this in half. So the surface tau equal constant is this surface. Okay. So this is tau equals 0. Tau equals 0. Okay. So okay, now I will not be able to draw this 3D perspective. So I'll just draw the circle that is drawn on the plane of the board. So what happens when I decrease? What happens to surfaces of constant Euclidean time when I decrease Euclidean time? Basically, what happens is that they become like that, like that, like that, like that, like that. So they converge here. So this point here is tau equals minus infinity. So if you go to Euclidean, if you look at this is AdS. Okay, you want me to be more precise? Yeah, I can be more precise. So okay, so AdS started its life here in x0 x d plus 1 x mu, and it was this hyperbola, right? Basically, this is seen from above, but you can make it more precise. There's some global coordinates, right? You can write x0 equals whatever, cos theta, and x, all the other x's, x mu, let's say x alpha equals sinh theta E alpha, where this E alpha, now it's a point on SD. Okay, it's a bigger sphere, and this alpha runs from 1 all the way to d plus 1. Okay, so this is, if you want, another set of coordinates that I still didn't introduce. So okay, it's the third one, which makes these pictures rigorous. So theta is some. It's what you see if you look from the top. So theta is the distance. Theta equals 0 is this point, and then surfaces of constant theta are these spheres. So this sphere SD is a sphere of constant theta equals to constant. Is this clear? Okay. So here I'm drawing this big sphere at infinity is SD, is when theta goes to infinity, you have this big sphere. And so this is the most global picture of Euclidean AdS you can have. Now in this picture you can draw the curves of constant tau, which is the other, what I was calling global coordinates. Okay, and that's what I'm drawing here. It's this kind of surfaces, and they converge to this point here. So this point here is tau equals plus infinity. Okay, I'd say, you see, it's very simple. You have this SD, you remove the north pole and the south pole, and now it's a cylinder. Okay, it's conformally equivalent to a cylinder. Okay, everybody understands what I'm drawing here? Because now the argument will be in pictures, so you please need to understand what I'm drawing here. Okay. So where should I write it? Miscalculated one board. So the argument is almost the same. Yeah, it's basically the same that you do for the state operator map in conformal field theory. Okay, so it's just direct adaptation of that to this case. So what is the statement? So suppose you are computing then some correlation function. So it will be you will have some operator O1 at point P1 and some other operator here, for example, O2 at point P2 and more operators, whatever, generic. And so, well, diagrammatically there will be some diagram, doesn't matter, that interacts all these particles, something, but doesn't really matter. So there will be, you want to compute this endpoint function. But now you want to replace, you want to do the OPE, so you want to replace these two operators, say O1 and O2, by a sum of operators at a given point. Okay, that's the notion of the OPE. You replace the product of two by a sum at a given point. So you go to that picture and you say, I'll compute this correlation function using quantization with respect to this foliation of constant tau surfaces. Okay, so the constant tau surfaces are conjugate to this Hamiltonian d by d tau, which is just the dilatation operator. So I will do canonical quantization with respect to these surfaces. So in particular, I can choose a surface here, which is tau equal constant, that separates these two operators from all the rest. Okay, so once I do that, it's clear that basically what I'm doing is I have all my other operators, and now in this surface I have some state psi that was created by these insertions, right? So I do the path integral just with tau less than this constant, and that creates some state psi on this surface. Okay. So now the only non-trivial question is can I create this state psi by computing the entire path integral, but now I create this state psi by placing a specific operator, O psi, at this special point, which is the point P of tau equals minus infinity. Okay, so this special point where all the surfaces converge. Okay, so this is the question: can we establish this state operator map? If we can, then we'll have an OPE, right? because we can replace these two operators insertions by some local operator that creates the same state in this surface. Okay, and basically the argument that this must work is the same as in flat space. So let's see. So in one direction, so operator creates state. It's obvious, right? You insert an operator, you do the path integral up to here. That will prepare some state on this surface. Okay? Now the other way around. State corresponds to operator. It's also obvious because you can move this surface using the dilatation operator, using the Hamiltonian, right? So you can just go to this surface, decompose into eigenstates of the Hamiltonian. Okay, that's some linear combination, and then you just prepare exactly that linear combination in some arbitrarily small cap around this boundary point. So this tau equals minus infinity point, and basically, since that's arbitrarily close to a point in the boundary, that's a definition of a local operator. So there's also a map from the state to a local operator. Okay, so that's just the same argument basically applied here. So there you are. So basically, I'm satisfying all the axioms of a CFT just with a conformal field theory in AdS. Quantum field theory in AdS, sorry. Yeah. So what's missing? Gravity. Why? But no. This is, I mean, I just want to do conformal field theory. Why should I care about gravity? No, you were right, but you have to argue better than that. Exactly. I'm missing the energy momentum tensor. So this is still not a CFT because it doesn't have an energy momentum tensor. So that we'll see next lecture. Thank you very much.
Kelsey, you talked about conformal field theory in AdS. So it's not necessary.
No, the theory in AdS does not have to be a conformal field theory.
Why do you talk about conformal
dimension? So the logic is like that. So any quantum field theory in AdS, just because it's on AdS, it will satisfy it will be invariant under the isometries of this space. Okay, so the isometry group of this space is the conformal group, is this SOD plus 1, 1. Okay. Now, if I put a scalar field with some mass m, then associated with that scalar field, there is an operator on the boundary, which is defined here. Okay, and this operator will have a scaling dimension delta, which is related to the mass of the scalar field. Okay, this was the relation that at some point I wrote, that mass squared in units of the AdS radius is the Casimir delta minus d. Okay.
But this mass is not that here
in the Lagrangian. Yes, it is. It is that mass. Yes. So the mass of the field in AdS is related to the scaling dimension of the operator defined by this limit.
That means you cannot choose arbitrary mass. Only coupled scalar AdS.
No. Like for a given mass, you will get the dimension of the operator.
So you first choose mass, and the scaling dimension is different from mass.
Yeah, you can think like that.
Presumably, if you want an operator that's not scalar or vector or something else, you just have the first one.
Yeah. Yes. So we'll see that to get the stress tensor, you will have to use a spin to a graviton. So, if you want to get a conserved current, you should use a gauge field. Yeah, there's. Yes.
In Lorentzian signature, if you were to go to a point-array coordinates, you have to worry about doing like a Bogoliubov transformation in the vacuum being different. Vacuum defines respect to global time versus quantum time.
Yes. So the right here I was talking about the spectrum of this dilatation operator. So this is the Hamiltonian conjugate to global time. It's not the Hamiltonian conjugate to Poincaré time. Yeah, that's true. So in particular, the Hamiltonian conjugate to Poincaré time does not have a discrete spectrum. It has a continuous spectrum. Yeah. No, good. So, no, I mean, so all these properties will only, I mean, if the theory in the bulk, if your quantum field theory is not UV complete in the bulk, then you also have problems, right? You will be computing things that will not make sense. But if it's a consistent quantum field theory in the dimension you are working on, then it will work. So that's an assumption here, right? So otherwise these diagrams, well, not these, but when you start putting loops, it will not be well defined, right? It will have divergence that you don't know how to renormalize. But I mean, that is. It doesn't work like that, right? Because like that, it would say, well, you can make a CFT with any dimensions, and you can just choose the masses and the interactions to create anything you want, right? And CFTs are much more constrained, right? Well, David showed you, like Bootstrap really constrains things, and that's because actually, when you bring in the stress tensor, the actual fact that it's a local theory, it's a much more constraining. It's much more constraining, yeah. Well, from the bulk is when you have to put gravity in. So, well, you can do some semi-classical expansion, but with gravity you don't know how to really do the full quantum story, right? Well, the goal of this talk or of these lectures is to convince you that to do the quantum gravity in AdS is to say that actually it's just CFT. It's literally equivalent. It's the definition of quantum gravity in AdS. It's CFT. Okay, but that's our next lecture. Probably it will be more clear. Yes.
I guess a follow up to that. So if you stick a effective field theory in the AdS bone, it won't be the boundary.
It will be, yeah. So good. That can be useful in some cases. It will not be exactly a conformal field theory because. So when you look in the operator product expansion, you will see operators with arbitrarily large dimensions. And for those operators with very large dimension, your effective field theory will be wrong. It will be computing their energies wrongly. And so it will not be a consistent CFT if you look at operators at very high dimension. But it will be approximately consistent within the low dimension operators. Okay? So that actually can be a good approximation to some physical systems. And I think, in a way, that's the spirit behind these applications to condensed matter and things like that. So you think of the operators that are more importantly for a given system, and then you write a bulk dual that realizes those operators, and you don't care too much about that you have a complete CFT. So in a way, that's a phenomenological way of constructing models that describe part of the system.
Is this story true or synthetic? Does it work
For I mean, it works in the sense that you get
I mean, does it only work for
you get the global part only. Yeah.
You don't, there's no, like, there's nothing nice happening with the verse or...
I think for that you need to put gravity, right? Because the Virasoro is generated by all these higher modes of the stress tensor. Yes.
Isn't some of the multi-trace operators also the primary as well, right?
Can you repeat?
Multi-trace operators are
Some
also
of them are primary,
right.
not all of them. Some
So,
of them.
right, yeah, not all of them.
Yeah.
So, I mean, I guess the single particle states definitely generate conformal family.
I should put one conformal family. The
One
multi-trace generate many conformal families. Yeah. Yeah. Clear? Because if you try this property here. So if you put alpha, so P equal to alpha, P. Now here I can multiply by and now we use alpha. And basically, because this thing goes to
It's
zero,
freezing.
You called it?
Or shorts. So
Yeah,
that's
like-
on me, but yeah, I think it's a little colder than the comfortable level.
I've never seen this argument of state up.
Oh, in the bulk?
Yeah.
Yeah, that's too. Yeah, that's nice.
so in Euclidean, before I was using minus x
It's a little.
all the other
So in this case, this went back to the Euclidean, right?
I think so, yeah.
So this sphere is the whole sphere, so it involves all the time in there.
Yeah, yeah.
If I send
Yeah, I guess
It's like having the cylinder, but then you also
pinches the top, and then those operators all on the
boundary.
Yeah, the cylinders. And usually when people see this within diagrams,
You think it's
like
a spatial slice or something.
Spatial
Yeah.
slice, I guess. Yeah, that's all right.
yes.
But I haven't seen like not like the version I think he has coordinates like up to
Yes, I think actually it's going to be further to like yes, this learning course it also has momentum. It's not just sections. Different ways of
right. So basically, you have for example
vectors have to be homogeneous, right? And that they have to be say orthogonal to the capital P coordinate, to the embedded space, right? So you also consider like kind of like a Klein-Gordon equation in the embedded space. Then you have like another algebra. Right? So you have like a P squared with xp plus px, which is kind of like scaling, right? And then you have like the homogeneity. So those three, I think, close to another algebra. So if you do not really have like
P is just P by dx.
right. So if you have, let's say, P, so if you have like if you have box squared, and then you have x dot p plus p dot x, which is like scaling plus the dimensionality, and then you have x squared equals 0, which will be like your p squared equals 0, basically like restricting yourself to the light consection. So the condition of restricting yourself to the light consection, homogeneity, and another one that would be like a box squared, but in the bigger dimensional space. Those three close to the algebra of SL2R. You see what I mean? So yeah, I think he uses that.
Yes, that's the problem. There's at the 6:30.
It's related to that, right? That you were using like box.
Well, it's funny.
Box. The Laplacian AdS can be written as box square, and then the scaling. So you're saying that you can box equals 0.
Right, and then you also, so if you have, then you have those three things that also form an algebra. Yeah. And that can be considered, I think what Professor Bars does is that he considers, so he's my advisor, right? So he considers that you have a phase space, so you have a gauge symmetry in phase space, and the gauge symmetry generators are exactly those three. So it's like your capital P squared equal to 0, so it's the condition of restricting you to the light consection. The x of p plus p dot x equals 0, which in your case would be like your it's basically your homogeneity, right? And then an extra one, which is like the box squared, sorry, the box acting on the field equals 0, but the box in the bigger space, right? And that basically, I mean, you can have like like in phase space, you can impose that as a gauge symmetry of the phase space,